Okay, so today's lecture is going to sort of flesh out our discussion of stock and flows and stock and flow dynamics, putting us in a position to discuss some of the mathematics beneath this in greater detail, and to get into some of the really powerful insights that can come when we characterize systems using these sort of tools, using stocks and flows, which map down to issues of differential equations, ordinary differential equations, and which will allow us to do things like solve for fixed points or equilibrium points for the systems in balance, identify situations where it's stable versus where it's unstable by analyzing some aspects of the situation, specifically the eigenvalues, and generally understanding where certain modes of behavior that are observed are coming from, with which feedback loops, for example, that are associated. So we're going to talk a little bit about today about higher order delays, equilibrium behavior. And I introduced this notion last time about structure shaping behavior. The idea is that the structure of a system, for stocks and flows that include presence of stocks and flows, how they're connected, and the relationships between variables within the system, what's connected with what, and through what relationships it's connected. That structure determines the behavior of the system. And one of the things that we see in these systems as an aspect of nonlinearity is that the behavior of the whole is more than the sum of the behavior of its parts. Okay, there's behavior coming from the system which we wouldn't anticipate from any one of its sub-pieces, and behavior with respect to input that can't be simply rendered or understood as very simple behaviors in response to very simple inputs. Okay, so when we have a nonlinear system, to relate this to this issue of decomposability and this aspect of nonlinearity, that the whole is different than the sum of the parts. When we have a linear system, let's here consider a system which is defined simply as a function. Okay. Now this function might be characterized using a simply enclosed form as a nonlinear function. Maybe it's f of x equals x squared. That's a simple nonlinear function, right? It's a function where if we give it alpha x as an argument, if this is a linear function, what is f of alpha x? Anyone tell me? Alpha times f of x, yes. And we could have a simple function like x squared, which violates this, right? F of x, alpha x, of course, being alpha squared times f of x in that case. That's one feature of a linear system. Another feature of a linear system is if we have f of a plus b, we can characterize that as what? Exactly. And this gets to this issue of decomposability. So those who are from engineering background will probably have seen a lot of focus from an engineering perspective in what are called linear time invariant systems. These are systems whose behavior doesn't change in some fixed way over as the course of time goes on, hence time invariant, but linear in these senses. And because of that, we can characterize input signals to these systems. Maybe it's a mechanical driving force for a mechanical system, or the force of wind in a structural context against a building, or maybe for an electrical system, it's a driving set of input. And we can analyze the behavior with respect to a very complex signal by doing what? What do we often do? Suppose we have a complex signal, maybe it's a square wave from a perspective of an electrical system. What do we do with that system to analyze the behavior of a linear time invariant system with respect to that? What do we do? We do an analysis of that square wave in terms of waveforms. So we we'll do something like a Fourier transform associated with that. Fourier transform basically characterizes that square wave as a sum of what? Sine waves, yeah, sinusoids, cosines and sines. And really what we're doing there is if we have some waveform, you know, some waveform, call it A of t, or call it x of t, so I'm going to speak sort of an input. Basically what we do is we take the dot product of this with various sinusoids, so we integrate this up times some, you know, e to the it, something like that, and this is an imaginary coefficient, and then we'll do it for different frequencies. So crudely speaking, what we're doing is we're multiplying x at t by some exponential, and we're summing it up. Just like with a dot product, we're doing, this is sort of a continuous analog to a dot product. Let me write this more easily. This is the I square root minus 1, right? J might be the frequency band of interest. We'll write it as omega as frequency, and then t is time. And so this is kind of similar to how we write a dot product of two vectors. Say if we have two vectors x dot y, we write it as the sum of x sub I and y sub I multiplied together. And that's essentially what we have here. The integral corresponds to the sum. The multiplication here corresponds to this multiplication. So essentially what we're doing is we're characterizing a waveform in terms of how much of each sinusoid is in it. We're considering it as a superposition of sinusoids, the sum of these things. And you've probably seen the pictures before. If we have a nice square wave, something like that, and we consider, you know, these things, you can imagine this as a sum of, you know, one sort of big mode like that, plus, you know, some higher frequency components, etc. And basically you figure out how much of each sinusoid is in there with a Fourier transform. You could do a Laplace transform and figure out how much of certain exponentials are present in there. And the reason we do that is what? Why do we analyze linear time invariant systems in terms of the inputs such as sine waves and such as well, using Fourier transforms and using Laplace transforms? Can anyone tell me from engineering background particularly? Why do we characterize waveforms in terms of those things? Because we understand the response very precisely of those systems with respect to each of those things. So if we have a sinusoid, it turns out with a linear time invariant system, we put in a sinusoid. What do we get out of a sinusoid, of the system? If we put in a sinusoid, we get out a what? We feed in a pure sinusoid at a certain frequency to a linear time invariant system, say a circuit with capacitors and inductors and resistors. What do we get out? A sinusoid. Yes. Yeah, different amplitude, but the same frequency. Same frequency. So, you know, here, if we're trying to understand the response of the system to a given frequency, we could kind of write it like this, and then we simply say, okay, this system damps out these frequencies in these ways, it amplifies these frequencies in that way. So all we do is we break up our input into frequencies, and we say, okay, we know how it's going to behave with respect to each of those frequencies, and we can then describe how it you know, ends up modifying what's the output for a given input. And we can do that because it's linear, because we can decompose an input here, folks, into these pieces. And we could say, okay, if we think of the input as a sum of sinusoids, A plus B plus C and so on, it's the response to that is simply f of A plus f of B plus f of C plus f of D, etc. So all we have to do is decompose it into sine waves, know how it behaves with respect to a sine wave of a given frequency, and we sum up the responses to each of those frequencies that's in the input, and we get out our output. That's the feature of a linear system. And turns out with nonlinear systems, we can't do that. So this would be for a linear system. When we have a nonlinear system, these features are no longer true. It typically will violate these properties. And that's why we can't simply decompose things. The behavior of the whole is more than the sum of the behavior of the parts. It's if we consider the behavior with respect to particular inputs. Maybe these are sine waves associated with some electrical voltage, but maybe these are interventions in a healthcare system, or maybe they're policies a company undertakes, and we want to consider how a company behaves in response to these. Or maybe it's a software project, and these are various actions undertaken by the project manager. Longer hours, rewarding people for finding bugs, encouraging people to take breaks to play foosball, whatever, having people do pair programming. If these are different interventions, different policies put into place, with a nonlinear system, we're not going to be able to just simulate its impact with respect to each of them independently and then understand its impact with respect to all together. We have to simulate them together. So nonlinearity plays out in all sorts of systems. In our system, we could characterize it as an f of x, sort of the output at a given time, but we can't really write down the f. We can't write it down at close point. Here we're going to stocks and flows, and the specification of the stocks and flows implicitly implies a certain behavior over time. It's just we can't write down what that behavior is over time. It's something that typically will defy our ability to turn them into closed form. So stock and flow structure of a system determines the qualitative behavior of the modes a system can take on. How does it behave over time? And unfortunately, unlike classic linear time invariant systems that you will have seen and studied, we can't simply define what that behavior is using a so-called transfer function, as you might have encountered in engineering. So we're going to talk about some elements. We talked about first-order delays last time. Can anyone characterize for me what's a first-order delay, as we discussed it last time? Characterize for me what a first-order delay is. What does it involve? What are some elements of a first-order delay? Speak, youths.
It involves a stop.
Good.
Whose value influences the flow into the
Okay, great.
Isn't it into the stop values?
No, there's a flow out of it, and it could be going to another stock, or it could be going to something outside of a concern of interest. But you've mentioned the key points. So there's a stock and there's a flow whose value depends on the stock. In what way? The rate of that flow depends on it in a way that is. So there's a rate alpha here, and that rate of. So this is a rate of chance per unit time of leaving, say. What is this flow? If we have this, what's the equation for this flow? Call the stock x. I don't like using the same axis down here. Call this stock y. Okay. So we have the stock y. What's the formula for how? So suppose this is measuring people. How many people per unit time go down here? That formula is given by what? Okay, it could be expressed as either y over alpha or y times alpha. Now, if it depends what the units of alpha are. If we're talking about alpha as a chance per unit time you're going to leave, it's actually alpha times y. If you're talking about a mean time till leaving, so chance per unit time of leaving, the units of that are what? 1 over time, right? Why this 1? Because a probability, it's like the fraction of time something happens, so it's dimensionless. It's, you know, whatever the thing is divided by the number of times that you get, you know, positive versus the total number of times you've tried, so the units cancel. So it's a this 1 over time. That 1 is dimensionless. It's a fraction. It's therefore it's dimensionless. It doesn't matter how we measure it. And then time in the denominator because it's per unit time chance. It could be 2, in which case it just means we're likely to go on average in half a time unit. Okay, so we could have an alpha whose unit is that, or we could have a mu, a mean time till leaving, whose unit will be what? Units will be what? We have mean time till leaving. I'm almost giving that to you. What's the units, folks? Time, yes, time. So, I mean, looking at this and knowing that the flow has to have the same unit as the stock divided by time, because it has that the stock is the integral of the flow times dt, so it's the integral of flow times some time. So you know that the flow, whatever unit the stock is, call it unit bracket y, then the unit of the flow is bracket y over time. Okay, so you know what this formula has to be. It has to be either alpha times y, that would be units y over t, or it has to be y divided by mu, mean time. In either case, you're absolutely right. These are constants. One constant is just the reciprocal of another. And that was something significant, ladies and gentlemen. And why was it significant? Well, it was actually something we derived, and there was actually quite a bit of math behind it. But the issue was that if we have a chance per unit time of leaving the stock, chance per unit time of moving on, transitioning out, our mean time in the stock is what? It's yes, exactly. It's 1 over. So, and that just comes out of the fact we can write it either way. We can write it as an alpha times this, or mu divided by that, and it turns out it's 1 over, one is 1 over the other. The mean time is 1 over the average time chance per leaving. And that, ladies and gentlemen, is going to be something that goes well beyond stocks and flows. We're going to actually see that relation in agent-based modeling. It's there in discrete event modeling, etc. So this first order delay is something which we're looking at as kind of its incarnation in agent-based and system dynamics modeling here, but we'll revisit it in different forms. So here we have our first order delay. And the first order delay was kind of the building block of many components. We're going to talk about some different components of it here. I'm going to go through this fairly quickly, okay? So the first component that I want to talk about is this component of, well, okay. Oh, yes, I should talk about this. Okay, so we have this stock. You're looking at that. You have your sneak preview. Okay, so here's your stock, and it exhibits a first order delay. We see this, we could just read it out. This is people times the annual risk of death. Note, ladies and gentlemen, that your chance of transitioning is independent of how long you've been here. That is the nature of the situation. Stocks are well mixed. They're defined in a way that we in no way are keeping track of how long someone has been in that stock. So the chance of leaving is independent of how long they've been there in that stock. Okay, it's memoryless, to put it another way. This is a memoryless transition process. You're kicked every time you have that same kick at the can for leaving, no matter how long you've been there. It doesn't care how long you've been there. That's associated with a Poisson transition process and an exponential residence time. Your time in that stock is exponentially distributed. You're more likely to leave sooner than you are to leave later. Your probability of still being there decreases more quickly early on, I should say. Excuse me. I restate that. your probability of leaving at a certain, of still being there at a certain time decreases exponentially. Your chance of leaving per unit time is always the same. Given that you are still in the stock, your chance per leaving over time is always the same. Your probability of leaving decreases exponentially like that. The number of people still in the stock, if it's still with 1,000 people initially, goes down in an exponential way. Most people leave early because there's more people to leave. But for those people still in the stock, they have the exact same chance per unit time of leaving during this period as they do this period, etc. Does that make sense to people? Okay. Okay, so we talked about the equilibrium value as well for the stock. And just to recall this, if we have an inflow rate of I, there's going to be some equilibrium value for the stock. And what is the defining characteristic of the equilibrium, folks? When I say equilibrium, what should you be thinking? What equals what? What's the equa in the equilibrium? Give me the equa in the equilibrium. Yeah, the rate of flow in is equal to the rate of flow out. The inflow rate equals the outflow rate. And from that, we can kind of trivially figure out this, this relationship of what the value of the stock must be. So if we have a chance per unit time of I of leaving, and thus an outflow rate of alpha times x, here y, and we set that equal to I, then the value of the stock at equilibrium has got to be equal to this. So it's a straightforward relationship. So if we had initially 0 coming in, and we have some chance per unit time leaving of 0.05, we're going to have a value here. I is 0, thus we're going to have an equilibrium value of 0. If we have no input in, if we had input an immigration rate in people per unit time of say 10, you'd have an equilibrium value of what? Your chance per unit time is 0.05. How long are you in the stock on average? Your chance per unit time of leaving is 0.05. You're in that stock for how long on average? 20. And the average number of people, the number of people in the stock at equilibrium, if 10 people are coming in per time unit, the number of people there at equilibrium would be you could figure it out mechanically as I over alpha, which is if there's 10 people coming in per time unit, I did say 0 initially earlier, but say 10 now. 10 people per time unit, it would be so it would be 20 times 10, so 200. But yeah, if it was 100 people per time, it would be 2,000. So here we would here we have this backup. Now you can also figure it out. I mean, it kind of makes sense because the average amount of time someone spends here is 20, right? So think about those 10 people coming in per time unit. It kind of has 20 time units worth of people who have accumulated during that time, right, before they leave. So on average, they're there for 20 time units. So 20 times 10 people per time unit, 200 is going to be on average. So it kind of makes sense. It accumulates an average of 20 units worth of people because that's the average amount of time till they leave. Does that make sense to people? Okay. So if we have an inflow, of different units, we'll have the stock. If it starts initially at 1,000 people, it'll either be rising to some value or declining. But this exhibits the features we saw before. It exhibits this goal-seeking behavior. Remember when we first introduced loops? What sort of loop was this sort of goal-seeking behavior associated with? This sort of stability was associated with what? A bouncing loop. And where's the balancing loop here? Can anyone see it? Don't make me do this too many times. Can anyone see the balancing loop? It's staring me right in the eye.
People's desk.
Yeah, exactly. It's people to desk and then desk back to people. And this desk to people is what sort of flow? Positive or negative? Negative, yeah. Because people to deaths is positive. The more people are at risk, the more people die. 0 people at risk, ain't nobody's gonna die. And if more deaths occurs, the fewer people there are in the stock. So this is a positive link going from people to death, a negative link from deaths to people. And so it's overall negative feedback, right? And hence this kind of this goal-seeking behavior. So it seeks some goals, and it's in fact it exhibits stability. More than that, we'll actually see in terms of the eigenvalues, this system will exhibit a negative eigenvalue associated with this loop. And what that means is it will damp down change, will damp down perturbation. If you perturb it, if you disturb this in some way from equilibrium, it will, suppose you had a sudden influx of more people that was short-lived. For sure, the number of people in that stock is going to go up, but then what's it going to do? It's going to, it was a short-lived influx. We gave it a square wave of people coming in just for a single, a boxcar function. It comes in for a brief period of time. Then what's it going to do? It's going to go up, the number of people in the stock, and then it's going to converge back to its original value. So it's going to kind of push back. Okay. So this is kind of our causal loop diagram associated with this. You know, if we change things, if we change input, for example, it will respond, and it will respond in a way that's fast initially, and then slowing down. So if the stock starts empty, it'll go up like this and go to some equilibrium value. Now, what's interesting is that if we have alpha to different values, so let's step back here. If we have 1 over alpha, excuse me. So if we have different time constants, here, which of these is the time constant? When I speak about a time constant associated with it, which of these is it? Is it alpha or is it mu? It's mu. That's the one measured at time. That's the sort of characteristic time associated with this stock. What we see is that a shorter characteristic time, so we're looking here, I should emphasize, I'm sorry, I should be clear here. What we're showing here is, I was showing here the stock for different inflows. If we change the inflow up to 100, it will sort of, the stock will accumulate. If we change the outflow or the inflow to lower values, the stock will go down. But let's take a look at this. Take a look at inflows and outflows. So if we think about our system, if we have an inflow that rises, what is the outflow going to do? Okay, suppose the inflow rises, the number of people in the stock is going to rise. What is that going to lead to the outflow doing? The number of people in the stock rises. What is that going to do to the outflow? Does the outflow depend on the number of, the rate of outflow depend on the number of people in the stock? Yes or no? Yes. And as this rises, is this a positive or negative link? Positive. So as this rises, what's this going to do? It's going to rise or fall compared to the value it otherwise would have had. Rise. Okay. And in fact, we can, and what, okay, folks, if this goes up from I1 to I2, what's the equilibrium value? So the stock is going to go up, and at what outflow will the stock be in balance again? The outflow will rise until what point? If the inflow is now at I sub 2, what's the outflow going to be at equilibrium, the new equilibrium? By definition of equilibrium, what's the outflow got to be? Equals. It's got to be I2 as well. So The question is how quick, right? So the stock goes up and the flow will follow, the outflow. Well, it turns out it will go up at a rate dictated by that time constant. Eh? So here it is for different time constants. So we have here the inflow going up at time 50. And not surprisingly, if we have a longer delay, that is mu is longer, that is 1 over alpha is larger, that is alpha is smaller, mu is smaller, chance per unit time, if you have something like 10 years or 20-year delay, that's in red, it'll take the outflow a significant amount of time to equilibrate. Imagine your population suddenly going up through immigration. It's going to take a while till the death rate really rises to fully reflect that new population. It takes for a while for people to age through, etc. By contrast, if we have something as small as a 2-year delay, this outflow is going to follow the inflow very quickly. Do you see that? Do you see that? The outflow is going to follow the inflow very quick. And this, ladies and gentlemen, is why you call this a first order delay. Because the outflow is a delayed version of the inflow. It's not perfectly delayed. It's not delayed in the sense that the outflow goes up after exactly 70 time units. It goes up, and it goes up at a rate dictated by the level of the delay, and it will take a certain average time till it's most of the way up. But basically it takes longer if there's a longer time constant, shorter if there's a shorter time constant. It's proportional to the time constant. Now the stock, meanwhile, is going up to different levels so as to drive this to equilibrium. The stock goes up to the level until the outflow equals the inflow. That makes sense? Yeah. So this stock is going up to the level where this is equal. So the outflow is a delayed version. So here, here we have a 2-year, 10-year, etc. Delay. Now, what if the stock doesn't start empty? For example, if it starts full, suppose there's no inflow at first. Well, it will decay down to a level approaching its new equilibrium value. If there's no inflow, what's its equilibrium value it's going towards? 0. And then suppose at time 50, we have some amount of input coming in, then it will start to rise accordingly. And this is different. This is with different time constants associated with it, I think. And this is for different initial values associated with it. Okay. So anyway, those are first order delays. The point is that we see this great stability associated with it, and we see sort of a characteristic delay of the input for the output. This seems very modest. It may seem very uninteresting, but what really starts to catch on is you start to put these things in process. This is uninteresting in the same sense that perhaps ones and zeros don't always inspire young minds. Here, however, it's how we put them together that makes all the difference, as in ones and zeros. So here we're going to use first order delays as building blocks. And we're going to move beyond this memoryless assumption. So with the first order delays, we assume the per unit time risk of transitioning out to the outflow is equal no matter how long ago someone entered the system. As long as you're in that stock, it doesn't matter how long you've been. You have that same kick at the can. Okay? Same chance of winning the lottery. Given that you haven't won it thus far. The problem is that for many cases, we know what transitions are not memoryless. It may be that there's some physical delays associated with it. Things fail after a certain amount of time of use, or what have you. After a certain amount of time, there's damage built up, or what have you. So we use what are called higher order delays, and hence going from first order to nth order. Okay, and these are very simple. They contain series of these first order delays. Okay, so we'll create what are called kth order delays. And they're just results of chains of these first order delays. The behavior of a kth order delay is a reflection of the behavior of first order delays out of which it's built, okay? And to understand this behavior, we're going to try to keep constant the mean time taken across them. So we're gonna compare the behavior of kth order delays, assuming that the mean time across them is held constant. Maybe it's held for 1, for example. Okay. So here's the first order delay. Let's suppose that, and for a first order delay, we said that the chance of leaving per unit time, given you haven't left yet, is the same. And the unconditional per unit time likelihood of leaving at between time t and t plus delta t is going to be changing over time for sure. You're more likely to have left it early on than later. So your conditional chance of leaving, given you're still there, stays the same. Your unconditional chance, your chance of having left it between time t and t plus delta t is changing, and it's going down in this sort of way. Your chance of remaining there. Here's the second order delay. So here we have 2 first order delays, but we're adjusting things so that we maintain the same mean time to transition across all stages. Okay. What will be the behavior, ladies and gentlemen, of this? Let me ask you this first. Is this memoryless? Is your chance of leaving via the stage 2 outflow independent of how long ago you came in? Anyone want to venture? So it's your chance of leaving per unit time, conditional that you haven't left yet. The chance of leaving is independent of how long independent of how long ago one came in. That people think that? Okay, so a bold suggestion. Anyone want to offer a counter position, a counter perspective? Anyone want to argue that it does depend on how long you've been there? Well, it turns out this is what we get. Likelihood of still being in the stock here, and the outflow is of this sort. So to be clear here, what I have going in, I should have made this clear. So the initial value of this was 1, and the initial value of this is 0. So we have a whole bunch of people here, and then no one here initially. And the question is, when do those people come out? So how many of those people come out immediately who are in stage 1? So we have a bunch of people here. We give it a value of 1 without loss of generality. When do those people come out on average? What's the average time till they emerge? This is the outflow. What do you think? What's the most popular time, the mode of the time that they emerge? What's the time that they're most likely to emerge? 10. Yeah, exactly at 10. This was a value actually, mean time to transition out of this says 50, but I'm not sure. I'm wondering if that's off. Do you perform this experiment? Okay, so 10 is the most average, most likely time. Most people take longer than that. This is not the median. This is not the time, less than which 50% have left and more than 50%. It's just the most likely, the mode. And then there's sort of this long tail on the upper side. Now this is in contrast. What would this be for a first order delay? What would this outflow be for a first order delay? If we drew this for a first order delay instead of a second, what would we see? We actually saw it before. It is this outflow. Someone there is most likely to have left in the first unit of time, and in the second, then in the third, etc. Given that they've remained there, their chances of leaving during the next delta t is the same. But overall, unconditionally, from an unconditional perspective, the chance of having left early on is higher. Here, their chance of having left early on is very small, in fact. And this is the total likelihood of still being in that state. It actually starts with, instead of declining exponentially, it starts with a bit of an inflection a bit of a, it's higher, and it's getting a larger and larger negative derivative, and then it comes on. So here's the third order delay. Still preserving the mean time across sections. What do you think this looks like? Anyone want to say? Again, everyone starting in stage one. What does this look like? Can anyone advance the theory? Yeah, outflow from the entire system. Yes. Yes, and I should have emphasized that. Thank you. Outflow from the entire system. What do you think that looks like? So if we compare it to this, does anyone want to hazard a guess? Yeah, average time across the system is the same. Where would there be a difference? Where would the difference be most pronounced, do you think? Where in this curve? Okay, yes. And why do you think at the start? Because they have to go further. They have to go through more stages. So there'll be fewer people coming immediately into this, into a situation where they can leave. And in fact, that's what we see. It kind of, this one has a lower slope initially, and then it rises, in contrast to this, where it's rising very steeply. We have this much bigger band. If we go to higher order delays, this is what we see. So first order, second order, third order, fourth order, fifth order, sixth order. Six is the blue. Are these getting closer to a certain distribution? Yes, a normal curve is emerging.
Is this a consequence of this central?
Yes, it's a consequence of the central limit theorem, because you have basically independent sort of chance of how long it's taking you through each of these different states. And it's taking, you're adding up, as you consider the order of the delays going up more and more, say to k, maybe k is 100, and you have a certain chance of taking a certain amount of time through that first one. Then a certain amount of time, it's quite independent of how long it took you to go through the first to go through the second. Another chance to draw out the third. So you're adding up a large number of independent probabilities. Now, a normal distribution is going to be extending a long way, and this actually has a minimum value, but it's approaching it closer and closer. And in fact, it is what's called an Erlang distribution. These are what are called Erlang distributions. Have you ever heard? Has anyone heard of Erlang distributions here before? Okay, yeah, it's named after the same Erlang, the great Scandinavian mathematician that was, I think, maybe engineer, that is behind the programming language Erlang, for those who aren't familiar.
I've been asked to post like camera distributions. Is that
Yes, yes. Erlang is a special form of gamma. Good call, young man.
Isn't normal also a special case of gamma?
Exponential is, I don't know, I don't think normal is, but I don't think normal. So, so the mean time of k stages, let's be very clear here. If we have each stage having a mean time of mu, what do you think the mean time of k stages is, each composed of small stages with mean time of mu? So if we have k stages, each taking mu on average, what's the time to cross k, all k of them? K times mu. Yeah, it's very straightforward. They're independent here. In our examples, as we added stages, we reduced the mean time per stage to keep the total constant. So I was doing that so we can kind of compare apples with apples. We could think of an infinite order delay. There's sort of a limit of this as k goes to infinity, and it actually approaches a normal distribution. And if we reduce the mean time per stage so as to keep the total time constant, in fact, it approaches an impulse function. So, in other words, if we aren't keeping the mean time across all stages constant, we'll get a normal distribution. We push more and more far out, k times mu as k goes to infinity, more and further and further out that the mean of it will be. And a normal distribution has infinite support. It goes both ways, and as far as the eye can see, and beyond. It goes to minus and plus infinity. But if we're shortening the amount of time so that the average time stays constant, in fact, it's going to be getting narrower and narrower and narrower until it's an impulse. Have people here, particularly from engineering background, seen impulse functions? They're also called Dirac delta functions. I think there may be heavy side functions, I think, different. Sorry? The integral? Okay, yeah. So the derivative of the heavy side function is the impulse function. And the impulse function is sort of the natural limit as one keeps these times, is one shrinks the total, the mu such that the total time is constant, or it yields the same constant value as we compare against k. So these are Erlang distributions, and yes, it's Erlang distributions, I think, are special members of the gamma family. K equals 1 gives the exponential distribution, first order delay. And k goes to infinity, not normalizing to keep it constant, it goes to a normal distribution, a Gaussian PDF, the probability distribution function. Okay, so as we sum these up, it's an aspect of the central limit theorem, and it converges. As we total up more and more things, the errors tend to cancel on average, and we get a normal distribution out in a way that's typical for large sums of large numbers of independent things. Generally speaking, we don't try to just put together kth order delays as a mean to capture a certain distribution, although that sometimes occurs. But often we'll represent, using these things, what are called aging chains, will represent stages. So this would be, for example, a diabetes model, stage 1 of chronic renal failure, stage 2, 3, 4, 5, dialysis, transplanted patients. These are stages of a condition that are recognized clinically. There's a clear meaning for stage 3, for stage 4. And there's timing that can be associated with them, your annual likelihood of going from one to the other. Now, so these are stages. And if we were to ignore these things going off down at the bottom, which represent risk of death, and these things going off at the top, we would have what's called a classic aging chain. Even this is what's called an aging chain, but without that it would be called an nth order delay. Here we have these competing risks. In other words, someone from stage 3 chronic renal failure could either go on to stage 4 or they could die first. Later stages, actually, there's opportunities for transplant as well. So let's talk about this issue of competing risks. And this gets into some subtle issues. So suppose we have a stock, and we have an outflow, so it looks like a first order delay, but we have two outflows. One going one way, one going the other. So suppose we consider, in this case, the outflow going straight down. Suppose that the chance of it gets higher and higher, the chance per year of going down this outflow just below the stock. Suppose that rises. How does that change our mean time to develop to go down this way, or does it? If we had no flow, if there's zero chance of going down this way, we have a mean time is given by this mu. This mu is related to the stock as this flow. The formula for this flow, that's a first order delay, is given by what? This is a first order flow, first order delay, and this is a mean time. What's the formula for this outflow? Dimensionally, what is it got to be? Okay, so there's a negative exponential associated with for sure in terms of how many people are going. But what's the formula? If I gave a formula for first order delay, the rate of this flow, how many people per unit time are going down there? How does that depend on the stock in the mean time? It is it's divided by the mean time. It's just the stock divided by the mean time. Linear, by the way. These are still linear models we're dealing with actually here. Nonlinearity we're going to see big time next time, okay? These are actually linear models. Why linear? they're complex. I mean, actually, it's hard to solve these intuitively, but they're actually linear relations. This is x divided by this guy. We're not multiplying the values of stocks yet, for example. We're going to get to that. We're going to get to where it flows. The rate, the chance of leaving per unit time depends on the value of another stock, like how many other people are infected. But let's suppose we have now the risk of going down here rising over time. How will that change our actually empirical mean time to get here? Or will it? Think of this. Okay, so 0, we have this mean time. Suppose we have a really, really high chance of leaving per unit time going down here. Will it change the average time taken for people who go down here? Yes or no, do you think? Yes. The answer is it does, in a big way. So basic dynamics are like this. So we have a decline in the diabetic population like this, and it looks very familiar. And that makes sense, folks. Can anyone riddle me this, people? Riddle me this, students. So give me the differential equation associated with it. Let's call the diabetic population x. Give me the differential equation. So dx dt equals what? Let's call this risk of mortality alpha. Let's call this risk of developing ESRD beta. Give me the formula for this. dx dt equals what? Good. Okay. Is there a missing sign? Okay. So yeah, if this is annual risk, if it's so this is a risk. So it's actually, if this is alpha, this should be x times alpha, because this is a risk chance per unit time. And then, but I know what you're saying is quite accurate. X over mu, or this is the mean time, right? And then there should be a minus sign, because they're why minus sign? Because they are.
I guess if it's a classic probability. Oh,
Well,
and time.
they're leaving the stock, so it's going down by the flow is out.
I'm just used to using constants that might be.
Oh yeah, might be
else.
negative. Yeah, yeah. Okay, fair enough. So if we see that equation written before us, x dot equals minus alpha x plus x over mu. You know, I object to this. I'm just going to write it as beta x. Solve for me this equation. What does this go as? Okay, and what's the solution for it? What's the solution? Yeah, exactly. Alpha plus beta times t, right? So in that case, it's just like, it just drained as if it's independently drained by each of these. But is your mean time to go to this other stock affected? And the answer is, yeah, it's affected, actually. So for the diabetics who progress on, if you have some baseline risks, you might have this blue curve. If you were to double those risks of mortality, you might have the red curve. Do you think the average time to go to cross this, if these are the number of folks going down to this population with ESRD, does the average time to go, do you think it changes between these two? The average time? No, we're just counting for those who do go down to the stock. What's the average time with which they do it? The answer is it does change. The mean time is changing, and in fact, we have this formula here, which we derived, and I go through the appropriate math here, but fundamentally, we have a formula here for the expected time to transition of alpha over alpha plus beta squared. Now, you could kind of argue that this has to be, because it's a mean time, and so its units have to be what? Time. In alpha and beta, what's their units? It's in with per unit time, so 1 over time. And so, you know, this is going to reduce time-wise to 1 over time plus 1 over time squared, which is 1 over time, which is time, okay? And it has to be symmetrical, right? I mean, because the underlying system is symmetric. We could ask the same question about going the other way. And moreover, it's got to be symmetric, so alpha and beta both have to be here in the denominator, and they're both for the same unit, so it makes sense that they're summed up there. In any case, we do have this alpha over alpha plus beta. So what this is saying is if beta increases, your mean time to progress along this continuum, your chance, your let's put it this way, your unconditional time until you reach here, given the fact that you've gone here, is in fact dependent on your chance of leaving down this. If you have a huge chance of leaving via death, the only people who are going to actually get here are people who go sooner, because there's going to be very few remaining later. And so it's going to put a premium on essentially those who are going sooner. And so it's going to shift that time earlier. In terms of, for those who actually make it, it's going to be earlier. If you have a very slow or none at all sort of death on this time, the mean time they can take as long as they would naturally to get over there. So this competing risks issue does actually skew the statistics here. And this is important because often we have data about this sort of system. We have data that's conditional. We don't have the luxury of data that takes into account everyone who's gone down this other path. Or instead, we're dealing with, say, the average time that it takes, the average time a car has been on the road or something like that. So for those cars on the road, what's the average time they've been on the road? And that doesn't take into account all the cars that have been jumped in the meantime. It's sort of those cars that are still on the road right now. What's the average amount of time they're on the road? So there's a lower mean time, and there's a mathematical explanation. There's a new intuition. At a higher rate of competing risk, a higher death rate, the population that's at risk of transitioning will decline very quickly, and so the only people to transition will be those in the first little bit of time. A lower death rate, you have longer luxury to go via that other stop. Okay, so those are competing risks. I want to use any questions about this? Any questions about this issue of first order delays, competing risks, and this issue of aging chains? Nothing yet? Okay, we're going to come to a topic within our next lecture or two, which has to do with delays and oscillations within these systems. We're going to see how those end up emerging as well. It turns out that when we have a system which exhibits not just negative feedbacks, but significant delays in the negative feedbacks, we may get oscillations. Instead of getting purely this sort of behavior, you may get situations where it overshoots, and then it overreacts, and you have a damped oscillation approaching the equilibrium value. Okay? That's associated with a long delay for the feedback. The feedback's operating to bring it back, to, raise it up, but it's not operating so quickly that, in other words, it's operating slowly enough that the feedback that it can sometimes go too high and then needs to react by going lower and overshoot again that way, and you get a sort of oscillatory behavior. That too will come out of some of the mathematics, and we'll see this applied within this next lecture. Okay, so I am going to go call up the this other thing, and this gets into This gets into some issues with infectious disease modeling, because this is a very nice example of the use of nonlinear systems, where you see systems interact. So dynamic modeling, it turns out, has a rich foundation that ties in with classic applied math. So linear algebra, calculus, differential equations, numerical analysis, control theory, and complex analysis all interface quite closely with some of the tools we're using here. Control theory being in large part sort of how do you effectively control dynamic systems, including nonlinear systems, and some of these other tools laying the foundations in terms of the methodology that we've already been applying. Turns out that that infectious diseases are a very nice example of nonlinear systems. And traditionally they include a variety of factors that are things like mixing between individuals, and this is where the nonlinearity will come in most directly, but also factors like aging, birth, etc. Preferential mixing, mixing contexts. And you get some classic phenomena of complex systems in terms of instability of these systems, nonlinearity, tipping points, oscillations, and multiple what are called fixed points in equilibria. Where have we seen an equilibrium already within this class? Where have we seen it within the past 15 minutes? We saw it for what? An equilibrium was associated with the behavior of what? Yeah, first order delays, right? Inflow equals outflow. It turns out that with these systems, we're going to have multiple equilibria, and the equilibria will be, will sometimes, under certain conditions, one equilibrium will be reached. Under others equilibrium will be reached. And there may be policies, for example, where we can nudge it from one equilibrium to another. So one equilibrium might be, for example, a disease like gonorrhea circulates at high levels within a population, and it's stable. Another might be that it's eradicated. And that also is something which is stable in the short term. But it may not be stable in the sense of if there were a perturbation, it's going to stay, it's going to remain in that state. It may go to the other state. So we can have these tipping points where we can wipe a disease out, for example, and there'll be oscillations associated with these. And so if we look historically, for example, a disease like chickenpox, this is classic for childhood infections, we see that there are these oscillations observed naturally. And these oscillations emerge from the nature, the stock and flow nature of the system, and the nonlinearity involved. So you'd have disease years where very few kids got chickenpox. There'd be a buildup of susceptibles, and then they would take off like wildfire. Okay. To really understand this, we'll see we can make best use of agent-based modeling, which is going to come in very shortly. So it turns out these oscillations are reflective of actually several types of loops. One of them is negative feedback loops, stock and flow considerations. So stocks continue, for example, to deplete as long as the outflow exceeds the inflow. Stock will rise as long as inflow exceeds the outflow. And it turns out that that can lead to long delays associated with these systems. And we're going to see this a key threshold, a key point which defines the equilibrium. So here's measles and chickenpox, both in Saskatchewan, and measles in mumps, for example, whooping cough, etc. And these things have been observed worldwide. So this is measles in England. Yes. 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 Yes.
Slowly builds up. Is that because there was a slow build up of people who were resistant?
Well,
That's
okay.
over a period
So
of years, though.
this is a period of years, and it's a very good question about what was going on here. I actually don't know the answer to why it was building up in that sort of way. I've got my theory in terms of mixing of kids and higher population densities, but it really is quite pronounced. But why this decline? Why this sort of pronounced cycles, and then around 1958 a decline to extremely low levels persistently? What happened in the 50s in Saskatchewan? Does anyone know? Yes, in rollout of what impacts childhood infections big time? Vaccines. Vaccines. And it's precisely because of vaccines, and that's why, you notice this, that's why I only show them through the 50s.
You should show these slides to people who are against vaccines.
Yes, I think it could be instructive. And, you know, it's interesting in England, I guess, so it looks like period 1948 to 68 prior to introduction of mass vaccination. So, you know, Saskatchewan was a world leader in some of these vaccinations. That's why those end earlier. Here, it leads up to it. And after that, it's a totally different situation. And this, ladies and gentlemen, is one of the great achievements of modern public health, is actually eliminating, because these conditions are not only nuisances, they kill children, and they can also later in life cause really bad harm to adults if they reach them. And one of the worst things that can happen is if there's incomplete vaccination, because then when you get the infection is typically later in life when the damage can be especially severe. So there's kind of, you want to go one way or the other, really thoroughly. And the nonlinearity of the system has much to do with this fact that it just dies out at a certain level of vaccination. Once a certain critical level of vaccination is reached, the behavior changes qualitatively. It goes, ladies and gentlemen, to a very different situation. You've reached a tipping point where you are now at a different equilibrium. You are now at a point where the dynamics of the system are very different. From a situation where, you know, a kid coming in could cause a mini epidemic, a mini outbreak, to a situation where it's like throwing a match instead of on tinder. It's like throwing it onto, you know, soggy moss or something. It's not going to spread. And it actually turns out to be a prescient analogy. We'll see that this analogy with kind of burning has a lot to do with it. Susceptibles being the fresh fuel, and recovers being charred wood. So tipping points have a lot to do with how the system responds. This instability is a result of nonlinearity together with stock and flow dynamics. So these principles of stocks and flows, principles of positive feedbacks, which have to do with the outbreak taking off, more and more infections, more and more infectives, more and more infections yet, and this sort of die down associated with drop-offs with depletion of susceptibles, will draw a lot on our stock and flow knowledge. It turns out the delays that we've just been talking about will play a key role in reasoning, why does this go on? Why doesn't it just go up to a level and reach some equilibrium, continue on? Why does it overshoot and then sort of collapse, overshoot and collapse, overshoot and collapse? It's because, in large part because the delays associated with it. Inflow and outflow are not in balance. And it'll sort of piece together these elements that we've seen with respect to the different components thus far. So we will see this as an example of a nonlinear system. And just to give you a peek of this, oh, by the way, there's gonorrhea. Just to give you a peek at this, these are the underlying systems we'll be using. Does anyone detect a difference from the sort of system that we've had here on the board, where we have something like y over mu, or y times alpha? What is different about this? Okay, so yes, we no longer have something just like this, where it's beta times s. But we actually have a situation where we have two state variables multiplied by each other, I and x. And this is what makes it non-linear. Ladies and gentlemen, if you have f, f of a comma b, and you want a purely linear system, you could have f of a plus b equals a plus b, for example. But if you start having a times b, we're going to start being in a nonlinear context. Here we have I times S, and it turns out that will make all the difference. It's almost as if your chance of transitioning depends on the value of another stock. And in fact, it does. Your chance of getting infected depends how many people are, it's not just how many people are at risk of getting infected, it's the number of susceptibles, it's how many people out there are infected. And so here we're getting into a situation where we're outside, we have at least some parts of the system, namely this first flow here, in terms of your likelihood of getting infected, that fall outside the realm of what we've seen with first order delays. It's kind of like we have a first order delay, but where the alpha is changing over time according to the value of different stocks. And in fact, it's changing proportional to the number of infectives. But meanwhile, here's our comfortable old first order delay for recovery. You have some average duration, some mean time to recover, and you have a first order delay going out of that. But you're going to have these nonlinear terms. And this is going to defy easy analysis. Now we'll also see why stocks and flows are so convenient for summarizing this. Because when we have a stock and flow, we can go from something like this, where one flow here that is a conserving flow, people going from susceptible to infective, turns into two components of this. This being one, this is the outflow component and the inflow component. Outflow with the minus coming from susceptible, coming out of here, and then the inflow going into I with this component here. And similarly, this first order delay, I over mu, is just the outflow here and the inflow there. So there'd be some underlying equations. And what we'll be able to do is to look at these sort of factors. So this is what's called a phase plot. Have people seen this before? Phase plots? State space plots? So this is commonly used to describe behavior of ordinary differential equations, particularly when we have fewer state variables. And if we plot number of susceptibles and number of infectives here on the two axes, now time is implicit here. We're not showing, there's no axis of time. Instead, over time, a particle, you could think of a ball, a marble that you've placed at the top of a mountain, and it's rolling down, and this is showing its path. Sometimes it's going faster, sometimes it's going slower, and here it reaches an equilibrium. In fact, there's a lot of sort of churn around here. Now, from one side of certain boundaries, it may go one way. In this case, the infection dies out, the number of infectives becomes smaller, and that allows recoveries to occur and eventually susceptibles to rise. Here we have a system which I should have shown it, but where recovereds eventually go back to susceptible state. But on a slightly different situation, say with slightly more healthcare workers, we have or slightly fewer healthcare workers, or slightly more infectives per healthcare worker, we could have a situation where the delays are such that the infection takes off, the number of infections skyrocket, and the number of susceptibles is reduced. So we'll take a look at this behavior in state space and how we can analyze these systems using the tools of applied math so that we can get an understanding of what the structure of the space is, what are the equilibria, and which of those equilibria are stable. That is, which of them will resist perturbation, which are robust, and which are fragile, in the sense that if one child with measles happens to come to the Saskatoon airport, there may be an outbreak. So we'll see how we can classify these equilibria, and we'll see in what ways policies might be able to affect that stability. Okay? So anyway, that's grist for the mill for the next lecture or two. Okay? And we're going to use this then to get into the whole agent-based modeling context, because it turns out that certain things will be quite a bit easier to understand and appreciate and easier to model within that context at a fine-grained level. Okay, so that's all for today. Thanks for accommodating